Have you ever stopped to think about the hidden genius inside the machines that make our world? I mean, we're surrounded by all these perfect objects, but we almost never see the incredibly simple, clever solutions that make them possible. Well, today, we're going to pull back the curtain on one of those unsung marvels.
So let's start with what seems like a simple question. How do you take thousands of individual threads and weave them into a perfect, flawless grid? Not just once, but millions of times with unbelievable speed and precision. You know, the very fabric you're wearing right now is living proof that we figured this out. You see, the answer isn't just about going fast. It's about solving a really tricky mechanical puzzle. It's a puzzle of movement, of timing, and of control. And every single piece has to be perfect with every single pass of the shuttle. Okay, so at the very heart of this puzzle is something called the shed. Just picture it. You lift one set of long threads up, and you pull another set down. That creates this little temporary tunnel. That's the shed. And through that tunnel, a cross thread, the weft, gets shot through. This simple action has to happen perfectly, thousands of times a minute. So how in the world do you create this shed with that kind of mechanical precision? Well, the hero of our story is this incredibly clever piece of engineering called the shedding tappet. Let's take a closer look at this thing. At its core, a tappet is basically a cam, an oddly shaped disc. But it's way easier to think of it as a kind of mechanical brain. Its only job is to spin around and around, but its unique shape translates that simple rotation into a very specific, very complex up and down motion for the threads. It's pure genius. And the anatomy of this brain is what makes it all work. First up, you've got the nose. This is the part of the disc that sticks out the farthest. As it rotates around, it pushes the whole mechanism to its highest point, which creates the very peak of the shed. And on the flip side of the nose, you have the heel. This is the point closest to the center, and it represents the lowest position for the threads. So that distance between the heel and the nose, that literally defines how big that tunnel for the weft is going to be. Now here's where things get really clever, the working face. This isn't just some random curve, it's a precisely engineered profile that connects the heel all the way to the nose. The shape of this curve dictates exactly how the threads lift, their speed, their acceleration, everything. If you get this curve wrong, you get jerky movements and broken threads. It's a disaster. And finally, we have the dwell period. This is a section usually right at the nose where the radius doesn't change, it's totally constant. So as this flattish part rotates, the shed is held perfectly open and perfectly still. This is the golden window of opportunity where the weft yarn can be shot through that tunnel with zero interference. So when you put all those parts together, the nose, the heel, the working face, the dwell, the tappet's shape creates this beautiful rhythmic dance of perfectly timed motion. Let's see how this all builds into a full cycle. Okay, in a typical 180-degree spin of the tappet, just look at how much time is dedicated to that dwell. About 65 degrees of the entire rotation is just for holding the shed wide open. The lift and the return phases are pretty quick, but that long, deliberate pause is the secret sauce that makes high-speed weaving even possible. It's a beautiful dance of action and absolute stillness. And the smoothness of that dance, well, it is everything. As this quote points out, any sudden jerkiness in the motion can instantly snap those delicate warp threads, bringing the entire massive operation to a grinding halt. So the shape of the tappet isn't just about creating movement, it's about creating incredibly gentle movement. So that brings us to a crucial design choice, the right motion profile. Most tappets are designed for what's called simple harmonic motion. Think about the smooth, predictable swing of a pendulum. It's perfect because it minimizes the stress on the threads. Now, you could use something like constant acceleration to go faster, but you're going to be putting way more stress on everything and risking a lot more broken threads. You know, this level of precision doesn't just happen by accident. Crafting one of these tappets is this fascinating process of turning raw math and calculations into a perfectly shaped physical tool. It all starts with picking the right stuff. For a really long time, cast iron was the go-to. It's durable, it resists wear, and it's pretty easy to machine. But for today's crazy fast looms, you need something stronger, like forged or alloy steels, just to withstand the immense forces. And check out this journey from a concept to a real thing. It starts with a carefully made wooden pattern based on all those mathematical designs. That's used to cast a rough metal blank, which is then put into a machine and milled down to its exact perfect profile. For the steel ones, it gets heat-treated to make it super hard, and then polished to a mirror-smooth finish so there's almost no friction. So, what's the legacy of the shedding tappet? When you look back, it truly became the absolute workhorse of the weaving industry, and for some very, very good reasons.
Its real genius is in its simplicity. I mean, compared to newer, more complex electronic systems, the Tappet is cheap to make, it's easy to maintain, and it's just incredibly reliable. When you have fewer moving parts, there's just less that can break. For churning out massive quantities of simple fabrics like plain weaves or twills, it was, and in many cases still is, absolutely unbeatable.
But of course, it's not perfect. That beautiful simplicity is also its biggest limitation. The return motion often relies on springs, and springs just can't keep up at super high speeds. They also get tired and wear out over time. This whole system, called negative shedding, just isn't the right tool for really complex patterns or the absolute fastest looms running today. But that doesn't take away from its importance at all. For decade after decade, this robust and incredibly efficient system powered the production of the very fabrics that built our modern world. It is a true, unsung hero of the industrial age, no question about it.
It really makes you think, doesn't it? The next time you pick up a simple piece of fabric, maybe you'll picture that elegant, oddly shaped disc spinning away, performing its perfect mechanical dance over and over. And it makes you wonder, what other simple inventions are out there? The hidden geniuses quietly shaping our lives every single day.